Hey guys, in this video we're going to cover section 9G. It's on expectation and it covers pages 19 to 22 in the chapter 9 note packet. So to begin, first scenario is if we have n trials in an experiment and the event has probability p of occurring in each trial, then the number of times we expect the event to occur is n multiplied by p. So if we just use E for expectation, we have our first equation to just do E equals NP. All right, first simple problem to demonstrate this is we have a goalkeeper with a 3/10 probability of saving a penalty attempt. How many would you expect to save from 90 attempts? So you really didn't need to be in Math Studies Chapter 9 to really kind of figure this out. But if if there are 90 attempts and I'm going to save 3 out of 10, then I should be saving 27 of them. So using the laws of probability, of course I won't perfectly do 27 each time, but the expected value is kind of like the idea in the long run. Next sample problem. If 3 coins are tossed, what is the chance that they all fall heads? Okay, so first a probability question. If 3 coins are tossed, what's the probability that they're all heads? So previous knowledge uses the multiplication rule for independent events. P heads times P heads times P heads, and we get 1 out of 8. So now part B, if we do this 3 coin toss 200 times, how often would we expect to get 3 heads? So if we go with the E equals NP idea, a chance process is done 200 times. An eighth of the time, we should get all 3 landing on heads, so it would be 25 times. Last sample problem here. If 2 dice are rolled simultaneously 180 times, on how many occasions would you expect to get a double? All right, well, expected value needs the probability of getting a double. So let's think this through. We know how to do this from a previous section as well. In a 2 dice being rolled, if we draw this grid, you would know that there would be 36 outcomes on this grid, and then you'd be able to count how often you get a double. So our doubles, I'm just going to use a highlighter for them, would be if we got, not there. If we got a 1-1, a 2-2, a 3-3, a 4-4, a 5-5, a 6-6. So the probability I get a double is 6 out of 36. That would reduce to 1 in 6 chance. So if I go with the E equals NP idea, if you tell me I'm going to roll 2 dice 180 times and a sixth of the time I should get doubles, I should get doubles 30 times. Okay, moving to page 20. All right, so when we continue the idea of expectation, next we have some experiments that are going to have numerical outcomes. So if the experiment is repeated over and over, we can find the average of the numerical outcomes. This average is called the expected value. So here's a blue box idea. Now we're going to change the expected value equation as follows. If we let the outcomes be the values x1 to xn, and the corresponding probabilities be p sub 1 to p sub n, then the expected value from the experiment is essentially a weighted average. We get the x value x1 of p1 proportion of times, plus x2 times p2, etc. So we have this expected value equation in this section to look like this. Okay, let's do some model problems for this. First, we have a spinner alongside. If we spin it and we get awarded the resulting points, on average, how many points would we be awarded per spin? So if we write this notation now in a summation symbol, of x sub I p sub I. Clearly it's a spinner where each number would have So when I solve for x, I'm just going to get x equals 30. So I have to increase Gold's payout to $30 for this to be a fair game. All right, this video is long enough, so the remaining problem right here, we could see it in the filled out notes. That's it. Section 9G. All done.